So we're going to start week 8 by talking about the cardiovascular system here. So this week we're going to do cardiovascular system, and then next week we're going to spend the first day talking about how exercise affects the cardiovascular system, and then we're going to talk about how exercise affects the respiratory system. And I think I misspoke. We're talking about the respiratory system this week. Okay, so here are the three objectives or outcomes that we're going to talk about. So we're going to talk about the oxygen cascade, and then we're going to talk about diffusion, and then just all the different locations that oxygen has to go through to get from the alveoli to the capillary. Okay, so we have something called the oxygen cascade. Now, if you remember, normal atmospheric pressure at sea level is 760 millimeters of mercury. Okay, and so this can change a little bit depending on what's going on with the weather, right? You can have high pressure and low pressure systems, but generally it's about 760 millimeters of mercury. Oftentimes you'll hear this referred to as 1 atmosphere. Okay, but you have to remember the atmosphere contains nitrogen and oxygen, as well as a little bit of CO2, a little bit of water, argon, and some other things. And so we're really only concerned about oxygen. And so in order to figure out how much oxygen is in the atmosphere, we take that 760 or whatever the barometric pressure is, and we multiply that by this 20.93%, because that's how much oxygen is in the atmosphere wherever you're at. Doesn't matter if you're on top of Everest, doesn't matter if you're at Death Valley, doesn't matter if you're in Utah or in Terre Haute or wherever. It's always going to be 20.93%. Okay? And so that gives us a value of about 159 millimeters of mercury. So at sea level, that's the pressure of oxygen in the air. Now, when we take a breath of air in, that air becomes humidified. Okay, and so we displace some of that air, some of that gas with water. Now, when air reaches our lungs, it becomes completely humidified. And the amount of water that can be held by air that's 37 degrees Celsius or about 98.6 degrees Fahrenheit is 47. And so we take that 760, we subtract 47, and now we multiply that by 0.2093. And so now that 159 that's in the atmosphere drops to about 149 inside of our alveoli. Okay, but wait, there's more. So by the time it actually gets into, I guess, from our airways into our alveoli, carbon dioxide mixes with the alveolar air and it displaces oxygen. And so we get down from about 149 to about 105. Okay. And then when we have blood that's leaving the alveoli, okay, so those pulmonary capillaries, we're now in those pulmonary arterioles, ultimately going into the, pulmonary venules, going into the pulmonary vein, we have the partial pressure of oxygen is about 100. Okay, now if you took Phys from me, and I'm not sure what happens if you took it in high school or in bio, they probably didn't mention this. They might not have. Generally, we just try and keep nice, easy textbook values. And so oftentimes we refer to this 105, we just say it's 100. And we say that the pressure in the arteries is about 100. Just say that there's essentially perfect equilibration. The problem is there isn't. And so we call this difference between the alveolar, which is P big A, and arterial, which is P little a, that difference in pressure, we call it the alveolar to arterial oxygen difference, or AADO2. Now, I came from the University of Oregon, and this was a big focus on the research that we did there, was just trying to understand what causes the AADO2. Okay? And there are 4 main things that we'll get into later. But one of those is diffusion. Okay, so in order for diffusion to occur, there's a couple of variables that we have to account for, or to understand the rate of diffusion, there's some things that we need to account for. Okay, so surface area, a diffusion constant, so every gas has a different ability to diffuse in water or whatever it is, the pressure gradient, and the thickness. Now, hopefully you can see that as we increase the 3 up here, if we increase surface area or that diffusion constant or the pressure gradient, the rate of diffusion will go up. Okay, but if we increase the thickness or just think of it in terms of the distance, that will lead to a decrease in the rate of diffusion. So if we're looking at oxygen uptake, it's the surface area where oxygen can diffuse times the diffusion constant of oxygen times the pressure gradient divided by the thickness. Now this especially is going to be really important towards the end of the semester when we talk about going to altitude. Okay, we have a reduced gradient at altitude, so it's actually more difficult to get oxygen inside your bloodstream. Okay, but you've got a few weeks to wait before we get there. All right, now, as you can see from this picture here, in order for oxygen to diffuse onto a blood cell, so from the alveoli into a blood cell, it's got to go through several different areas. It's got to cross the alveolar wall, then the alveolar membrane, then the capillary membrane, then the capillary wall, then the red blood cell membrane, and that takes a lot of time. This isn't something that happens instantly, but it takes time. And we're going to talk about that next week, about just what's called transit time and diffusion time. So diffusion time is how long it takes for diffusion to actually occur, but transit time is how much time is actually available for diffusion to occur. Okay, so that's something to look forward to later on in the in this unit.